The collision theory of reaction rate, Cambridge IGCSE Chemistry. We will progress through simple collision theory, through reaction profiles, concentration and pressure change and the effect on rate, the effect of surface area on rate, and then temperature change and its effect on rate. Remember, learning is an active process, so take notes, complete the tasks by pausing the lesson when you are requested to. Chemical reactions involve a change from reactants to products. The rate of reaction could be counted as how fast a reactant is used up, or counted as how fast a chemical is formed, how fast the product is made. Collision theory is used to explain changes in how fast reactions occur, that is, changes in rate of reaction. For a reaction between two particles to occur, simple collision theory uses two main ideas. The first one is that particles must collide. The second one is that the collision must possess a minimum energy. Collisions that have that minimum energy and result in a reaction are termed successful. Collisions that do not result in a reaction are unsuccessful. An important point is that the vast majority of collisions are unsuccessful. Reaction pathway diagrams. Consider reactant A and B forming product C. So we can map this on a reaction pathway diagram. Here is the energy of A and B. Here is the energy of the product C. Now, there's an energy barrier between A and B and C. The difference between their initial energy and the top of that reaction pathway curve is termed the activation energy. That is the minimum energy required on collision for those particles to react. If they do have that energy, they're able to progress to form C. If they don't possess that activation energy, they would return to the original states, A and B. So if they possess the activation energy, they can progress over the reaction pathway curve and form product C. The vast majority of collisions between A and B, however, do not possess the activation energy. The vast majority return to form the initial reactants A and B. So, having set out the main ideas of collision theory, we now move on to concentration and pressure effects and attempt to explain those effects using collision theory. So let's consider the effects of increasing concentration. We have two types of particles in my diagram, a blue and a black. They are both in solution. And as such, they are moving randomly in a fixed volume at a fixed temperature. Collisions occur at a fixed frequency. So the rate of collisions per second is steady. If you increase the number of particles in this fixed volume, so if you compare my left diagram to my right diagram, I've got more particles, more blue particles and more black particles. Well, there's an increase in the collision frequency. That is, there are more collisions per second, given that the particles are moving randomly. So we conclude that an increase in the concentration, that is an increase in the numbers of particles in a fixed volume, leads to more collisions per second. So let's put the explanation of higher concentrations and their effect on increasing rate of reaction into three simple progressive statements. I'd like you to pause the lesson. What logical sequence of three statements leads to linking higher concentrations to higher rates, or explains the effect of higher concentrations in producing higher rates? Pause. What are the three things you need to link together? Come back to check and correct when you are ready. Okay, so the first thing we need to say is a higher concentration means more particles per volume. That, of course, leads to more collisions per second, a higher collision frequency. And therefore, there are more successful collisions per second. If there are more collisions, although the vast majority are unsuccessful, if there are more collisions, then there are more successful collisions per second. Of course, the argument for lower concentrations is simply a reverse of the arguments for the higher concentration effects. Moving on to effects of changing gaseous pressure. So, same format as the previous slide, two types of gaseous particle, a blue and a black. In a fixed volume, at a fixed temperature, they are moving randomly. Of course, collisions occur at a certain fixed frequency, a certain fixed number of collisions per second. If we increase the number of particles in the fixed volume, so I've got more blue particles and more black particles, then of course we have more collisions per second. The collision frequency increases. So that means we've got more collisions per second. We call an increase in the number of particles in a fixed volume an increase in pressure. So to summarize the effect of changing pressure on a gaseous system, please complete these four statements. A lower pressure means less, which results in therefore there are less effective collisions, needs to be completed. So a lower pressure results in again, complete the statement. Pause, complete the four statements, come back to check and correct when you are ready. Okay, so a lower pressure means less particles per volume, which results in a lower collision frequency. Therefore, there are less effective collisions per second, per minute, per unit time. So a lower pressure results in a lower rate of reaction. Surface area effects. Here is a reactant particle. Its surface area is the bold black outline. Now, if we divide that particle into smaller particles, then we'll see that we can increase the total surface area. By dividing, we've put on a line here. Here, we've increased the surface area here, here, here. All of this is increased surface area. Therefore, if we compare the surface area available for collision between the particle and other reactant particles, well, then we can see that there's a much greater surface area available for collision with other reactant particles if we divide into smaller particles and increase the total surface area. So if there are more collisions between reactants per second, then increasing the surface area also increases the rate of reaction. Of course, the reverse argument applies if you reduce surface area in one way or another. So here is a problem from typical exam question. Compare and explain the differing rate of the reaction between small marble chips and dilute acid to that between the acid and the same mass of large marble chips. Typically, this would be for about 3 marks. Pause, write an answer that will be credited with 3 marks, and come back to check and correct when you are ready. Okay, so to reveal, given the same mass, marble chips, small marble chips will have a greater surface area than the large marble chips. Therefore, there are more collisions per second between the small chips and acid than between the large chips and the acid. Therefore, the rate of reaction is greater for small chips than for the large marble chips. Explaining temperature effects on rate using collision theory. The key effect of temperature change is to change the movement or kinetic energy of the particles. So if we start with the idea of increasing temperature, that increases the movement, the kinetic energy of the particles. Don't forget, from collision theory, for a collision to be successful, the colliding particles must possess enough energy. However, most collisions are unsuccessful. So if we look at this pie chart of collisions, the vast majority of the chart is grey, unsuccessful collisions. There's a small portion, a small percentage, a small fraction of the collisions are successful. But at higher temperatures, a greater percentage, a greater fraction, a greater proportion are successful. So increasing the temperature leads to an increase in the rate of reaction. How is this explained? Come up with 2 statements, 2 ideas that are linked. Write them down. Come back to check and correct when you are ready. Okay, so I'm going to reveal my linked ideas. There's an increase in the property of the particles as the temperature increases. That, of course, is the kinetic energy. If the kinetic energy of the particles is increased, so more of the collisions possess the activation energy and are successful. Note, raising the temperature also causes a small increase in collision frequency. The particles are moving faster. The reverse arguments, of course, apply to reducing temperature. Remember, you are in control of these lessons. If you wish to repeat any slides, please do so. Otherwise, move on to try some textbook questions and then pass paper questions from the correct exam board. Thanks very much for watching. If you liked, please like, please subscribe.